In this video, we'll consider one example on design of FIR filter. Design an FIR filter for the following desired frequency response. H of omega is equal to e power minus j3 omega if omega is less than or equal to pi by 4 and its value is 0 elsewhere. Use Hamming window function, obtain the frequency response of the desired FIR filter. So in this example, desired frequency response of the filter is given, that is hd of omega is equal to e power minus j3 omega. First let me draw, that is magnitude frequency response of desired filter, desired low pass filter is shown below. That is, just I will draw the frequency response. Say this is hd of omega, this side is plus omega and this side is minus omega. Let this be the origin where omega is equal to 0. So here it is said that the response is e power minus j3 omega if omega value is less than or equal to pi by 4. Here magnitude is shown, that is for plus, this is, we'll assume that this is plus pi by 4 and assume that this is minus pi by 4, and it exists only between minus pi by 4 to, and its value is 0, that is greater than pi by 4, that is greater than pi by 4, its value is 0, and here also it is. We know that the desired frequency response is usually represented as hd of omega is equal to e power minus j omega tau. So now in this example, comparing this expression with this, we can say that therefore tau is equal to 3. So this is we have obtained from the given expression. Now we know that in FIR filter, tau is also equal to m minus 1 by 2. So here tau value is given. With the help of tau value, let's calculate m. Therefore, this leads to 2 tau equal to m minus 1. So therefore, m is equal to 2 tau plus 1, that is 2 into 3 plus 1. Therefore, m is equal to 7. So here m is order of the filter. So the now next step is we have to find inverse Fourier transform of this given frequency response, so that we will get hd of n. That is taking inverse Fourier transform of hd of omega. So inverse Fourier transform of hd of omega is represented as hd of n, which is equal to 1 over 2 pi integration minus pi to pi given hd of omega e power j omega n d omega. So one should remember this formula. So now we'll try to find hd of n, which is equal to 1 over 2 pi. So here we can observe that it exists only for minus pi by 4 to plus pi by 4. So the lower limit is minus pi by 4 and upper limit is plus pi by 4. So therefore I can write minus pi by 4. Here it is plus pi by 4. The value of hd of omega is e power minus j3 omega. Same thing I will write here, e power minus j3 omega into this e power j omega n, I will write as it is j omega n into d omega. We'll simplify this further. That is 1 over 2 pi integration minus pi by 4 to pi by 4. So here I will take e power j omega common. e power j omega n minus 3 into d omega. Now we'll take the integration of this, that is 1 over 2 pi. Now taking integration of this, it gives e power j omega n minus 3 divided by j n minus 3. So now I will apply the limit to this, that is minus pi by 4 plus pi by 4. To simplify this, I will simplify here. So that now I can write, therefore hd of n is equal to 1 upon 2 pi in bracket. We are supposed to apply the limit, that is e power j, omega is the variable, we should replace omega by this value, that is pi by 4 in bracket n minus 3 minus e power minus j pi by 4 of n minus, so divided by, here we have j n minus 3, that is j of n minus 3. Here also we can write j of n minus 3. So further I can represent this as hd of n is equal to 1 over 2 pi. So here we can write j n minus 3 e power j pi by 4 of n minus 3 minus e power minus j pi by 4 of n minus 3. Now further I can simplify this as hd of n is equal to, so here I'll take n minus 3 out of the bracket. I will write it as 1 upon pi. I will keep it as it is. I'll take this n minus 3 out of the bracket, n minus 3, and I will represent this 2 inside the bracket as 2j, and the numerator will be, I'll keep as it is, j pi by 4 of n minus 3 minus e power minus j pi by 4 of n minus 3. We know that e power j theta minus e power minus j theta divided by 2j is equal to sine theta. So here comparing this expression with this, we can say that theta is nothing but pi by 4 into n minus 3. Therefore I can write hd of n as, so therefore hd of n is equal to 1 upon pi of n minus 3 into, we have this sine theta, where theta is pi by 4 into n minus 3, that is sine pi by 4 into n minus 3. So therefore I can write hd of n is equal to pi by 4 of n minus 3 divided by pi of n minus 3. We'll call it as equation. Now in this equation, in equation 1, if n is equal to 3, then we have hd of n is equal to sine pi by 4, we are taking n is equal to 3, that is 3 minus 3 divided by pi of 3 minus 3, which is equal to 0. We know that sine 0 is 0, 0 by 0 form, that is, so now we are supposed to solve this using L'Hospital rule. Using L'Hospital rule, we know that limit alpha tends to 0, sin a alpha divided by alpha will be equal to a. We'll call it as 2. Now compare equation 1 and 2. Therefore, equation 1, that is hd of n, can be represented as sin pi by 4 of n minus 3 divided by pi of n minus 3 is equal to pi by 4 divided by pi, that is nothing but pi by 4 into 1 by pi, that is 1 by 4, which is equal to 0.25. So hd of n value is 0.25 for n is equal to 3. So now therefore I can write in general hd of n as hd of n is equal to sin pi by 4 of n minus 3 divided by pi of n minus 3 for n is not equal to 3, its value is 1 by 4 for n is equal to 3. So here hd of n is the impulse response of the system. Now we are supposed to design the filter using Hamming window. So let's write the Hamming window sequence. Hamming window sequence is given by the Hamming window. Let's write it as hm of n is equal to 0.54 minus 0.46 cos of 2 pi n divided by m minus 1 for n is equal to 0, 1, 2 up to m minus 1, and its value is 0 otherwise. So now to design the filter, here hd of n is an infinite sequence. So it is necessary to truncate it to get the finite sequence. So to truncate it, we are supposed to multiply this hd of n with the Hamming window sequence, that is wh of n, so that we'll get h of n. Therefore, we know that next step is we are supposed to calculate h of n, which is equal to hd of n into whm of n. So therefore, I can write h of n is equal to hd of n is nothing but sin pi by 4 of n minus 3 divided by pi n minus 3 into Hamming window sequence, that is 0.54 minus 0.46 cos 2 pi n divided by m minus 1. As we know, here m value is 7. 7 minus 1 is 6. We'll call it as equation 2, equation 3, 3, 4, 5 and 6. That is m minus 1. Here m value is 7. So 0 to 6. We find the impulse response, that is h of n, for different values of n. For easy calculation, I will make this table. Here hd of n is this is hd of n. This is hd of n, and this is Hamming window sequence, that is w, that is whm of n. So here I have written hd of n, which is nothing but this expression, and whm of n is nothing but this expression. I will solve these two values separately, then multiply hd of n with whm of n, so that I will get h of n. So for n is equal to 0, substituting n equal to 0 in this equation, hd of n gives 0.075. One can solve this directly by substituting. One can solve this directly using calculator. So WHM of n for n equal to 0, it gives 0.08. So multiplying these two expressions will get 0.006. Similarly, for n equal to 1 in this expression, it gives 0.1592. Multiplying so substituting n equal to 1 in this equation, it gives 0.31. Multiplying these two will get 0.04929. Similarly, for n is equal to 2, will get for n equal to 2, hd of n gives 0.2251. For n equal to 2, WHM of n gives 0.77. Multiplying these two, it gives 0.1733. Similarly, for n equal to 3, we'll get 0.25, which is already we have calculated. And for n equal to 3, here we can see that 2 pi into 3, that is 3 divided by 6 is 2. 2 will get cancelled. Cos pi is 1. So 0.54 minus 0.6. Substituting n equal to 3 in this equation, it gives 1. H of n is 0.25. Similarly, for n equal to 4, we'll get 0.2251. Here we'll get 0.77. Multiplying these two will get 0.1733. Similarly, for n equal to 5, we'll get 0.1592. Here we'll get 0.31. Multiplying these two, 0.04929. And finally, last value, that for n equal to 6, we'll get 0.075, 0.08, 0.006. So here we can see that h of n is symmetric with m is equal to 7. That is, we know that the symmetry property says that h of m minus 1 minus n is equal to h of n. That is nothing but h of, here m value is 7, that is 6 minus n is equal to h of n. Here we can verify the result. If we take n equal to 0 here, h of 6 value is equal to h of 0, that is h of 6 and h of 0 are same. Similarly, if we take n equal to 1, that is h of 5 is equal to h of 1. H of 5 and h of values are 1. Similarly, h of 2 and h of 4 are 1. And this value is for n equal to 3. Now we'll calculate the frequency response of symmetric FIR filter. The frequency response of symmetric FIR filter is given by, this is the formula to calculate frequency response of the symmetric FIR filter. So now I will calculate it as h of e power j omega is equal to e power minus j omega. M is 7, that is 7 minus 1 is 6, 6 by 2 is 3. I can write it as e power minus j 3 omega. We have here h of m is 7, 6 by 2 is 3, plus expanding this summation for different summation n is equal to 1 to, here m value is 7, 6 by 2 is 3, 2h of m is 7, 7 minus 1 is 6, 6 by 3 minus n into cos omega n. So solving for different values of n, that is h of e power j omega is equal to e power minus j 3 omega h of 3, plus for n equal to 1 it can be written as 2h of 2 into cos omega, plus for n equal to 2, 2h of 3 minus 2 is 1 into cos of 2 omega, plus for n equal to 3, 3 omega. Now substituting the values, that is h of e power j omega is equal to e power minus j 3 omega. So h of 3 value is 0.25 plus 2 into h of 2 value is 0.1733 into cos omega, plus 2 into h of 1 is 0.04929 into cos of 2 omega, plus 2 into h of 0 is 0.006 into cos of 3 omega. So simplifying this further, I can write h of e power j omega is equal to e power minus j 3 omega 0.25 plus, multiplying this we get 0.346 cos omega plus 0.098 cos of 2 omega plus 0.0012 cos of 3 omega. So this is the frequency response of the symmetric amplifier filter. Thank you for watching.